Firstly, I'd like to thank all of you for attending this is our third webinar, which we're doing monthly. And this webinar is about ground penetrating radar and how we use it within the testing industry. So we were asked by a number of our clients and viewers to explain more about GPR and its merits, hence this presentation today. So we at HGA would like to get a clear message across to engineers, consultants and asset owners of the range of non-destructive testing and investigations that are readily available today. So recently we've seen a number of high-profile asset failures, including bridge and building structures, and these appear to be occurring more frequently across the globe, such as in Mexico City earlier this month. These failures are reportedly due to two main factors. Firstly, aging infrastructure reaching the end of its design life, and a lack of regular inspection and investigation programs to identify defects. And secondly, poor quality construction, including materials and methods. So in the UK, there have been a number of prominent structures that fall into the above categories, with Hammersmith Bridge being a great example, reported in the national news on more than one occasion. At HGA, we believe it's vitally important to share industry information, technology, experience and case studies in an attempt to debunk the NDT myths that have previously and are still clouding our industry. So today, Henderson Thomas's director, Warren Thomas, will be presenting on the following. So what ground penetrating radar technology is available, which is known in the industry as GPR, the applications of GPR, mainly with respect to structural investigations, importantly, the limitations of GPR applications, and successful case studies carried out by HGA. As many of you will be aware, GPR is one of an array of tools which the testing industry have in its toolbox. Unfortunately, many believe it is the only tool you need. However, the following presentation will show you that this is not necessarily the case. As Warren's explained, we'll have a Q&A session at the end of the webinar. So please type in your questions into the chat function or email testing@hendersonthomas.co.uk or email Warren or myself. So we hope you enjoy this presentation. Again, if there's any topics you'd like HGA to discuss at future webinars, please let us know by email or telephone, and I will hand you over to Warren to give his talk on GPR.
Good afternoon, everybody. Hopefully you can see the screen. And as Steve kindly informed you, I'll be doing a presentation on GPR. Just as a brief introduction, bit of a history on GPR. The first patents were issued at the turn of the century, around about 1910. There was some further developments around in the 20s, but to be perfectly honest, there really wasn't very much development of the technique until the 70s, and that was initially driven by military applications in the US. Round about the early 70s and into, I think it was the mid 70s, were the first commercially available bits of equipment that we could actually use in the field. Very much the initial applications of ground penetrating radar, or impulse radar as it's also known, were to do with ground investigations and soil investigations. From the 70s through to the current day, there's been a massive growth in the application of the equipment, the different types of equipment that are available to everybody in our industry. And we at HGA are now utilising a number of bits of GPR equipment, more for the structural investigation side of things to do with buildings and bridges and other civil engineering structures. However, we still do use radar for the initial applications that it was used for service locations and sub-ground investigations. And as you can see on the bottom of this list, a bit of a strange oddball application that we were asked to do some time ago was the detection of missing whiskey. And when I say missing whiskey, it wasn't stolen whiskey. It was to do with the angel share, which is the evaporation of whiskey in a barrel over a length of time. We have been using ground penetrating radar since the conception of the company. And I must at this stage thank two companies, or three companies really. GSSI are an American-based company who have produced a large number of pieces of equipment which are extensively used in the UK and the US. And their supplier is Allied Associates, who have given us a lot of training and advice over the years. Equally, some of the more newer equipment that's been on the market over the last 5 to 6 years has been manufactured by Prosec, a Swiss company, who we have a very close working relationship with. What I would like to say is these are just two manufacturers of the equipment. There are other manufacturers, to name a couple would be Hilti and Leica. We're not really singing the praises of the equipment manufacturers, more the technology and how we can apply this in the civil engineering market. How does it work? I'm not going to go into too much detail into the technology. You can read very much large amounts of tomes of this on the internet. But effectively, the radar equipment emits a high frequency electromagnetic energy into the material you're looking at. What you will find is there will be varying dielectric constants, which is a GPR term, and these will vary between different objects that you're looking at. And to just give you a very quick idea, air has a dielectric constant of 1, water 81. And these laws of physics dictate how we can actually pick up and detect objects within concrete, which is what we're primarily going to be talking about today. So here we have a radar set on one of our test blocks. As you can see on the left-hand side of the slide, the dielectric of concrete is around about 4.5 to 5. The dielectric of the embedded reinforcement in here is massively, from a variant from that. So therefore, the dielectric change between concrete and the embedded reinforcement is very large. So as the text at the top of the screen says, the larger the dielectric change, the stronger the reflection and the brighter the target. So this is why, in the first instance of what we're looking at here, ground penetrating radar is has a very good application against detecting reinforcing bars in steel. Going on from this, and I'll talk about this a bit later in the presentation, you will see that the smaller the dielectric change between materials, that will be more difficult to pick up. So just very briefly, if you were trying to pick up a clay pipe in clay soil, because the dielectrics are so very similar, it may prove to be problematical to get as good a result as we're seeing here, where it's steel in concrete. At this point, what I would like to say is one of the, as I've already discussed, primary applications that we use and a number of the industry testing houses use in the UK and in the rest of the world is to use GPR to detect reinforcement within concrete, as explained previously. One of the things I'd like to put out there straight away is we're asked, and I'm sure there's a number of people out there who are in the same boat, that we're asked to do a ferroscan survey. There is no such thing as a ferroscan survey. A ferroscan is a type of equipment. What we need as testers in the industry is a clear and concise specification of what you require as a building owner, asset owner, civil engineer, structural engineer, architect, or whatever. Therefore, in our experience, a cover meter survey really falls into two categories. The first one is to determine the depth of reinforcement within concrete as an indication of the protective alkalinity of the concrete and the depth of concrete protection over the bar. So that type of cover meter survey is really linked into what is the depth of the reinforcement and how much concrete is protecting it. That comes under what I would call a concrete condition testing survey and is part of a suite of tests that we would normally carry out. Secondly, and what we're asked to do probably more on a regular basis using GPR, is an assessment survey of concrete elements, slabs, columns, and beams. Here, the client generally needs to know the configuration of the reinforcement within the said element and its depth, but more importantly, the diameter of the bar and the accurate diameter of the bar, and in a lot of cases, what type of bar it is. So for instance, if we're looking at concrete, you can generally get round plain bars, which are generally mild steel, or you can get ribbed, deformed, square twisted bars, which a lot of these are generally high tensile. All of these things, to get definitive answers, you must break out and expose the bar. There's a lot of misinformation from a number of people, firms, and manufacturers of the equipment that say you do not need to do this. One of the statements is you can get plus or minus 1 bar size. And I've asked a certain manufacturer, well, are you talking about metric bar sizes or imperial bar sizes? And they don't know. And then when you ask them what type of bar is present, they don't know. So generally, the applications of NDT, be it a cover meter or be it a radar, has a limited approach when you actually need to know the exact diameter of the bar and the type of the bar, and even the exact cover of the bar. These are all only inferred with a percentage error, which means the actual survey will be very limited. Here are just a couple of case studies that we just like to show some photographs. On the left, you can see Steve carrying out some radar work on a very large post-tension elevated section of motorway that goes into London. Here, the radar was used as a cover meter to detect where the rebar was, but in addition, it was used to detect the location of the post-tensioned tendon, which previously to having this type of equipment available was very difficult to detect. The photograph on the right just shows a roof slab that we were asked to look at. And here the client did have no drawings as to the construction details. So he wanted to know if the concrete slab was just conventionally reinforced or had steel encased beams, and we were able to do that from the roof. And it also meant we could determine if there was any screeds on the roof slab, and it allowed us, in this case, just to tell them what type of construction without having to break out the roof membrane. Going forward, the photograph on the left-hand side was a post-tension beam on a site in Scotland where the client actually knew there was a major problem with the grouting process that hadn't actually been carried out very effectively. So we needed to locate the exact location of the post-tension tendon ducts so we could do some other investigatory works and then allow the client to drill into the tendons that were voided and allow a grouting program to go ahead. The photograph on the right is a slab investigation that we carried out. As I said, where you get variations, good variations on the dielectric constant, these can be picked up, given the right site conditions, very well on site. And here we found that the GPR equipment that we were using could actually quite accurately pick up voidage within a slab. And in this instance, underneath the slab. What had happened on this was a gas refinery slab, which was very extensive in its extent. And they were bringing on a 75-ton crane to do some maintenance works. And their main concern was they'd actually locally found that there was some washout of the fill material underneath this slab. And the client's concern was running a crane over it would mean that the crane could potentially topple over and cause millions of pounds worth of damage. So we went round with this, proved the areas, and what we found on this occasion was the voidage underneath the slab was very much linked in with the drainage system that had been put in place underneath the slab. But it did mean we could give green walkways all the way around the site for the crane to go on. This is, as I said earlier, probably one of the more strange applications for GPR. What we're getting here is, and if anybody drinks whiskey and knows about the angel share, the angel share is a story that's been produced up in Scotland. And effectively what the true thing is when the whiskey is put into a barrel to age for anywhere between 12 and 40 years, due to the humidity and the temperature and the porous nature of the oak barrels, a lot of evaporation of the whiskey will occur. And so this client actually wanted to know exactly how many bottles of whiskey he was going to be able to bottle off of all of these barrels. And this is something I know that has been largely used in the US as well. So again, just really outlining some of the applications. The scan on the right-hand side, what you're actually seeing there, and one of the myths that we're trying to debunk is we want our clients and our asset owners to see these scans and for us to clearly identify what is going on. So effectively what's happening here is you have got two layers of reinforcement, and the reinforcement is being indicated by this parabolic target. So that's a bar here, that's a bar here, and here, and here. And you can see a second layer that's lower down. At this layer here, what is intimated on the plot at 21.1 centimeters is the back wall echo of the slab. Now, this is all based upon dielectric that's been input to the radar set. So we're basing it on a dielectric. Concrete, unfortunately, is not a completely homogeneous material. And therefore, for you to accurately determine what exactly is going on with respect to depth, you do need to carry out some calibration. So what we've been asked to do in a lot of instances is to take a core through the slab. We generally are then asked to crush the core for compressive strength, which is something else the client normally requires. But what it means is we can then scan directly above or adjacent to the core hole, and where, if for instance, to give you an example, if the core is actually 230 millimeters thick, we can actually calibrate the scan here to 230 mil. That means the equipment will have been calibrated to the exact dielectric of the slab in question, and we can then scan across the rest of the slab. And if we get variations in the slab thickness, this will be a true representation of the thickening or thinning of the slab. And it does mean you can scan large areas with minimal calibration. Here on the left-hand side is a scan going through a bridge deck. So the top 130 mil is intimated as being the black top. There we then have a waterproofing layer. This white layer can sometimes indicate a small gap. We tend to find that that white layer is indicating an air gap bit, quite small. Then we have the concrete, and you can see clearly 3 rebars indicated on that plot. One of the applications that we've massively been using radar for in the last 4 or 5 years is to help us ascertain post-tension condition of bridges and car parks and buildings. What we had to do in the past, prior to these structure scan minis or the GPR Live that we've been using, we would have to just go with conventional electromagnetic cover meters. They have a very limited range of only about 100 mil depth to pick up details. So it would be good to pick up the reinforcement within concrete, but not to actually pick up the profiled nature of a tendon. And these are the sort of standard of the drawings that we would originally receive. And we would then have to go off of the drawings to ascertain the exact location of the tendon. The problem is drawings are all well and good, but as we've found in the past, I'm sure a number of people out there have seen, they're not massively accurate. And so what we have to do is we cover meter the area to try and work out where the bars are. However, if the rebar and the tendons are in close proximity, we really can't determine which is which from using a conventional cover meter. We will then mark that up on the concrete surface at a said location that the client wants us to investigate the tendon. And this tends to be what we've called the stitch drilling process. It's time consuming. There's high hand-arm vibration, dust, vibration to the structure, and damage to the structure, which isn't really the way we want to go forward. If we can reduce the amount of intrusive works, we'd like to do that. So going forward with GPR technology, and this is, sorry, just to show you, this can be the amount of damage that we cause. So here you can see on the right-hand side, a number of drill holes taken to try and locate the tendon duct, because the tendon duct's at depth and we can't locate that with a conventional cover meter. And as you can see on the left-hand side, that is the sheath that we've encountered with a couple of drillings. So with discussing with the manufacturers of the equipment and seeing how we can utilize it, this is now the new process that we utilize. So by using GPR, we can locate accurately the tendons, and we can differentiate between the tendons in the concrete and reinforcement. To give an example, here we have a live scan that was done on a post-tension structure not that long ago. So again, what you've got here is the parabolic targets at the top are the reinforcing bars. The size of the elements you're looking at can be determined by the horizontal spread of that parabolic target. So what you can see on the top of the slab is they're a lot smaller than the three far wider and less steep angles of parabolic targets, which we're now identifying here. These targets that have been estimated to be at a depth of 270 mil were the three tendons that we were looking to investigate on this particular bridge. It means that we can very accurately locate the tendon. We still have to normally carry out a calibrationary drill hole to encounter the end of the sheath, after which we can either break out or take a core to expose a longer section of the duct, and then we can do more intrusive works to find out what is the corrosive condition of the tendon and its grouting nature. Oh, sorry. So this gives you an idea of what you would actually see on site. So the photograph on the right-hand side shows in the white chalk the actual profiled tendons, their location, which as you can see is not straight. They will be profiled throughout the length of a beam or a slab. And in the yellow chalk, you can quite clearly see the reinforcement. This allows us to do, as I said, a pilot hole to locate the tendon and then to overcore. And as you can see, that's exactly what we've done on the photograph on the left hand of the screen. This is actually a video of this is the GSSI unit being used in anger to detect the profiled nature of the tendon in a post-tension beam. It's vitally important that we know where the tendon is within the beam, because as you can see, it will vary quite dramatically along its length, which is clearly indicated here. Just some other case studies. The slide on the left-hand side is of a culvert that we had to try and identify its location. Here we actually used deeper penetrating radar to pick up a far deeper element. The small bits of equipment that you can see sitting on the barrel of whiskey on the right-hand side normally have a penetration depth of between 500 and 600 mil. What you can certainly do is utilize other equipment which will penetrate deeper. All I would say, and again, people need to be aware of this, the equipment that penetrates deeper, the definition of what you can pick up is reduced. And this is why the small sets that we use for structural investigations are only limited to 0.5 metre, but they give us a great deal of detail, as you can see on the scans that we've shown you. Whereas as you penetrate down to 2 metres and deeper, the elements and objects you're trying to pick up are generally larger in nature. And here we have on the left-hand side a photograph of a jack arch, which has been formed with metal beams, and the scan on the right-hand side shows the metal beams clearly shown here as these parabolic targets. What was quite interesting here is the client thought that these beams actually ran the other way, so we found that they were completely running a different way, which had quite an effect on their design of the structure going above this. Most of what I've been discussing has been detecting metal objects within concrete. However, as I intimated earlier, because of the dielectric of air is quite distinctly different from the dielectric of concrete or soil, it can be very good to pick up voids within concrete. And in this instance that we're showing here, underneath the concrete slab, and what we were seeing to do is, having taken some survey work, drilled a hole through the slab. And as you can see, this is a rising tide coming right the way through the slab. Drilling these holes, though, allowed the owner of this slipway to actually inject underneath the slab to show that it was fully supported by the area underneath it. We've seen a pretty classic example of when slabs can be undermined with the failure of a dam up in the Midlands, which nearly flooded a town nearby. So these are investigations that need to be carried out to ensure structures are still in the condition that they were constructed in. I briefly touched on some of the limitations of the technique. But like any technique, it's vitally important that the limitations are known by ourselves as the users and our clients. As I've already intimated, materials of different dielectrics can be picked up lovely. And here you can see a scan that we did over a jetty on the Thames, where we could clearly detect these bars within the concrete. However, if, as I've said, the dielectric constant is similar, you will have problems. As I said, the clay pipe and the clay material. Also, clay soils, because of the increased moisture content, become more highly conductive. That highly conductive nature of any material that we're investigating will attenuate the GPR signal. And effectively, the signal is absorbed by the material very quickly, meaning its penetration depth is massively reduced. A couple of good examples are using GPR on a newly cast slab. Because the slab will have a high moisture content, the effectiveness of GPR to pick up rebar and such like will be massively reduced. Whereas if you come back in 6 months' time, when the slab has time to cure, using GPR to pick up defects can be very, very good, because the slab has dried out, it's become less conductive. Another sort of real problems with GPR is if you have high salt levels in any of the material, generally in the soil, that again can make the attenuate the GPR signal massively. And because of the variation in dielectric between steel and concrete, we can pick up bars. However, if you have a very congested nature of bars within concrete, that can be a major problem of trying to detect anything further into the concrete. And we come on to a very good example of what we saw quite recently. We were asked by a client to have a look at concrete slab that had been constructed with, it was a fibre reinforced slab, and the fibres were actually metallic. So what happened is, as the slide is showing here, the GPR system emitted the energy to go into the concrete, but it was reflected off of all the steel work, and we couldn't find anything beyond that. The reason that they were initially using GPR was on this particular project, there were large voids that had been detected when they were drilling some anchors in to hold the racking system was going up about 10 meters high. So they were very concerned that these very extensive voids were present to the slab. We went there with 2 or 3 radar sets just to double check that that was not the right technique or technology. And again, we were found wanting. And this is why I'd like to stress, and Steve touched on it in his introduction, when you ask somebody to come out onto site, and when we go out onto site, we will have a number of tools in our toolbox. Radar will not solve every problem you have. And this is a classic example. Here, we had to use ultrasonic technology to determine the void in the concrete, where radar just wasn't the right technique. And this is, to give you an idea, this was the detail we were trying to pick up. But because of the large congestion and bunching of these fibers, which caused the voidage, it meant any radio wave was just reflected off of that, and we couldn't pick up any of the air gaps underneath. And we were fortunate enough to receive a couple of slabs which we use as testing. This is a little video that so you can see there's no way GPR signals are going to get through this. And that's why you do have to think about the technology and its limitations. Thankfully, they're few and far between, but they are there, and we do need to ensure that you as the end user, well, not as the end user, but you as the person getting our reports, realise that. Okay, thanks very much. Hopefully you found it interesting, and I think Steve's going to interject and see if we've got any questions.
If I unmute. Thanks very much, Warren. Yeah, we've got a few questions here that I'll read out. First one, roughly how accurate is GPR with respect to thickness of a concrete suspended slab?
Again, there is a element of, you will have an element of error, which could be 10, could be 20%. What we are trying to do is trying to get across to people that you do need some type of calibration a lot of the time. So if you're looking at, I think, Steve, you were on site when we drilled the tendons on that scan. They were around about 280, 290 deep, weren't they? Yeah, they are. I mean, I've done a couple of jobs where you don't want to actually puncture right through. But we have proved, you know, say it's like a 250, 300 mil thick suspended slab. It's usually plus or minus 5 mil in a decent quality concrete. So it's quite accurate, but you can't rely on it for that data solely. Yeah, I mean, it comes back to a bit like what we were talking about. We do cover meter surveys. I know that a variation of 1 or 2 mil on diameter makes a massive, massive effect on a load bearing calculation for a structural engineer. Equally, if we're 5 or 10 mil out on the thickness of a concrete slab, it may or may not have a major effect. Therefore, what we always stress is if definitive is required, there does need to be an amount of calibration. We are trying to reduce that, and certainly using GPR, for instance, for slab investigations. Years ago, we'd be asked to go and cut 30, 40 cores on a massive slab to determine any variations in thickness. We can now reduce that down to 1 or 2, calibrate the readings. We may need to take some more cores, but what we can certainly do is reduce the length of the core, because I do not really want to produce problems with a slab by breaking through waterproofing membranes under it. So it's not there yet to say you don't need to do any calibration, but we're massively reducing the amount of destructive work that we need. Yeah, and just add to that, there's some instances obviously where we can't actually do any intrusives, you know, if the asset owner doesn't want it there to be a repair there. So
we'll do spot checks with like a cover meter, so we can, cover meter is a bit more accurate, picking up that reinforcement, and then we can relay that onto the GPR unit, change the dielectric accordingly, and then that gives us a good calibration point. The next question's kind of been answered, like, do you always recommend calibrating GPR results? I mean, we would, yeah. You got anything more to add on calibration, Warren?
No, I mean, the whole thing about the dielectric constant, if you have exactly the right dielectric constant in the machine you're using, it should be very, very accurate in determining the thickness of a slab. But the problem is, as we've said, you can actually test the same concrete in different areas, and if it's wet, you'll get different readings than if it's dry. So this is why, you know, it really is strongly recommended by ourselves to have some form of calibration. Like I say, we're trying to reduce the amount of work down to the minimum, and I think that's being adopted well by clients. But it is that answer: is it definitively 300 mil or 310 mil thick? We would not be able to tell without any form of calibration.
Yeah, we've had someone else on the chat say that in their experience, usually have an accuracy of 5 to 10 millimeters. So similar to us. Thank you for the input. Next question, Warren. Do energized buried electricity cables cause GPR scanning limitations over and above the metal in the cables?
We haven't had masses of experience doing service locations surveys, but certainly the GSSI, I know, for instance, do a dual frequency unit that is extensively used for services. So I think we would have probably heard, but I could be incorrect here, if there was major issues with a cable that had electricity running through it. I mean, I think it's the material type that we're looking at. But again, we could certainly go back to someone like Allied and just check on that. But yeah, I mean, what we'll do is we'll make a note of that question and maybe come back to the individual if they'd like to leave their email or phone number for us.
I mean, only last week we were out on site. And, you know, a lot of the time we're trying to cut cores and do other work. So we use the GPR a lot, not to specifically locate services, but to basically knock core into them. So we are picking up a lot of cables, and we were picking up what was known to be 4 high voltage electricity cables, and they showed up quite clearly. So I've never had anything completely ruining the data, but yeah, it would be an interesting one to look into further. I agree. So we've got a couple more questions, so if you have got anything else, just type them in now. Have you had much success using impact echo for locating post-tension ducts in bridge structures?
We haven't personally. The technique for locating the tendon duct, we use radar, because radar, the whole physics behind it is having a large extruded aluminium sheath with lots of pre-stressing tendons going through it is a really big target for us to pick up. We have experienced it by far to be the best method of finding tendons within concrete. The other technology that we're using, as I said, was the ultrasonic pulse velocity. That technology was the technique we used to find the void on the concrete slab that you saw at the end of the slideshow. And we've used that very successfully. Steve Hughes used it a lot to find voids within tendons, which when I started doing this years ago, the only way you could determine any problems with the grouting system was to do x-rays, which are very, very sort of expensive and cannot be applied generally to our sort of the work that we're looking at. What we are trying to do is to try and look into some other techniques that are out there and to see how effective they are. But we're generally the two big ones that we're looking at the moment is GPR for finding the tendon. Once we've found the tendon, then we use ultrasonic pulse velocity, or also known as tomography, to determine if the tendon has problems with its grouting.
Yeah, so the sort of impact echo and the ultrasonics, you know, they give about 60% reflection back from steel. So it does kind of pick the tendon up, but it's a lot clearer in terms of just location with GPR, we've found. All right, here we go. We've got another couple have just come through. Does the percentage of the angel share increase following a site visit by Warren?
I wish it did. I wish it did.
I think in terms of questions, I think we have one more. How long have you been using GPR on structures?
The first time we actually used, it was a Structure Scan Mini, and it just been released by GSSI, and we hired it off of Allied Associates. Was on the Huntingdon Rail Viaduct, and that must have been probably 10, 12 years ago. We were asked there to ascertain the condition of the concrete on the webs of the bridge, because they were going to jack the bridge up and strengthen it. And it was the first time that I'd actually used it in anger. And that was the first time that I'd actually ever seen and ever was able to detect tendons. Prior to that, we'd used radar back in the, I'm trying to think, I used to work at Stangers, Harry Stangers, and we did use radar back in the, I must have been early 90s, with limited success on trying to pick tendons up. Again, a couple of bridges we were looking at on the M25, they had a very, very congested amount of reinforcing spars, which with the equipment back then had limited success. So there has been a great deal of development on the techniques. We've got lots more buttons on the boxes that we can use, for want of a less technical term, to really calibrate the equipment and help us to try to detect the targets we're looking for. So we've been using radar for a number of years, but more effectively with the smaller bits of kit that you've seen generally in the presentation. I would say 10 to 12 years. And what I would say is we're still learning, which is great, because the applications that are out there that we don't even know about. And if anybody says they know everything, I would clearly say they don't.
Just with reference to the energizing of the cables, we've just had a bit of input from one of our attendees who I know is very experienced in GPR. So they've actually had have had no experience of that making the GPR less accurate, and what we need to add is a few of the, like ProSet one that does have it, I believe GSSI as well, have a live cable detector locator on them. So, you know, they are used GPR to find these live cables. So we don't feel that it does have a major effect negatively on the results. And we have one more question, Warren. So have you tried identifying concrete defects in the top of a bridge deck without excavating the asphalt, typically looking for delamination, although identifying separation of waterproof membrane?
We did a number of years ago, and again, because of the equipment that we're using, it was a bit of trying to use a sledgehammer to crack a nut. What we have been able to do in certain instances is determine delamination of materials, because, as we were saying, where you get an air gap, it's a distinctive change of dielectric constant. And so if there is a gap there or there's a water layer there, these are things that can quite accurately be picked up by radar. So if you have a failing waterproofing system where water's getting underneath it, you can scan using the equipment that we've been talking about. And because I spoke about the attenuation of the signal due to water, that dampening or blocking of the signal into the material can indicate. But again, you have to calibrate, because it could be a number of things that that could be indicating these variations in dielectric. The first time we actually used this, there was a slab in London on a London Underground station where effectively what had happened is a screed had been laid onto the top of a concrete slab years and years ago, and we found that there was settlement of the pad foundations, and it dropped by about 25 mil, and so there was this gap around which mirror imaged the exact cross-sectional area of these pad foundations. And I used the GSSI Structure Scan Mini to do that, and found that we had really good correlation with you could actually hit it with a hammer and hear a hollow sound. And the company, they had to sort of vary the remedial measures they were going to do, putting footpaths through this because of this void. So if we get a big enough air void, we could potentially pick up things. Radar's great going over blacktop because you can scan and pick up. I don't know if you want to maybe just briefly explain what we did on the elevated motorway section, Steve, that we were doing, because there you were finding tendons underneath.
Yeah, so we were looking for tendons at the high point, so over the piers. Obviously, there's more chance of there being less grout or no grout at that point. So we were, around the piers, you often get more reinforcement. And what Ron was explaining earlier is it kind of sometimes masks the image, but we were getting really good readings in between the reinforcement, picking up exactly where the bank of 3 tendons, which were over a web. And really, when we were doing a number of these over weeks, the first few we were drilling them just to check they were there, but we actually got confident enough to just spray up the trial pit straight away, excavate it, because we actually had to go in and do the test the actual waterproof and test the concrete and open the tendons. But yeah, we're getting a lot of good confidence finding them from the top of the blacktop, which is I think the blacktop on that was about 200 thick. These little radars go to 500 to 700 mil, so usually on a bridge deck you're not getting more than that. So in that respect, it did work very well.
I mean, what I would say with a lot of the applications of radar is what we tended to try and do certainly over the last 24 months is the number of applications that we're using it for has grown quite dramatically. However, if someone does come up to us and say, will it do this or will it do that? If we haven't had the experience, we'll be quite honest and say, we don't know. And what we normally do, and we've been doing this very recently, is say, look, it will either come out and do a trial, or we'll just come out and do a one-day visit and attempt to use a number of bits of equipment to determine what you're looking for. And I think this is the biggest question that isn't asked by testing houses. You've got a problem. You're talking about failure of a waterproofing system, debombment of the blacktop and such like. If we're given that clear information, if that's what you want to pick up, we can then come along with, as I've said earlier, maybe more than one bit of kit. The classic is we found there were some voids within a shotcrete repair on a bridge, and we came along with radar because we thought that might work. It did, and then we calibrated the radar reflections we were getting where it would appear we were getting voids, and we tested that again with tomography, and the two calibrated lovely. So it meant we then did some investigatory works, and it all bore fruit. That's what you need to do. I think just calling somebody out, just saying radar is going to do the job. The question has to be asked by the testing house. What exactly are you looking for? What is the end game that you want us to actually tell you? And I think that gets lost a lot of the time. I don't know why. We're always asking, and if people don't, we're being nosy. Well, that's part of our job. We want to make sure if we come out on site, we're using the right kit. And this is why you can see radar is very good, but in other instances, you will get limited information from it.
Yeah, I think that's a good note to end on.